So question 5.20, there's a throttling valve, which gas is flowing through, coming in with a pressure of 1.2 megapascals and a temperature of 20 degrees Celsius. Assuming the velocity is the same at the inlet and the outlet, what's the exit temperature and the area ratio between the inlet and exit? So this is our first throttling valve question. So a throttling valve is just a device that lowers the pressure of some fluid. That's the only thing it does. So how do we want to look at this? Well, to find the temperature, we're probably going to want to look at the first law of thermodynamics to see if there's something about the enthalpy that helps us with the temperature. And for the area ratio, we're going to want to look at conservation of mass, because area is always, well, the only real information we get about area comes from the conservation of mass. So let's start with the temperature and the first law of thermodynamics. So first law of thermodynamics, Q dot minus W dot equals M dot change in enthalpy. Ooh, actually, let me erase that. Sorry, M dot change in enthalpy. Change in kinetic energy, change in potential energy. Okay, so change in potential energy, it's this horizontal valve, so this is 0. We're told the inlet and exit velocities are the same, so this is a 0 here. And for throttling valve, there's no work done in the throttling valve, and it's adiabatic. So both heat and work are 0. So this, what we end up with is 0 equals M dot change in enthalpy, or just the change in enthalpy is 0. So this is a feature that is characteristic of these types of valves, of these expansion valves. And the feature is that it's an isenthalpic process, which means, of course, that the enthalpy stays the same from beginning to the end. So this result that we're getting here makes sense. If we just manipulate it, you get H2 equals H1. But what does this tell us, of course, about the temperature? Well, for an ideal gas, we know that the change in enthalpy is Cp delta T, so T2 minus T1. And we know that the change in enthalpy is 0. So T2 minus T1 equals 0, T2 equals T1. And we're told in the question that that's 20 degrees Celsius, like this. So that's the answer. It's the same temperature because there's no work, no heat, and that's what we end up with. And it's the same enthalpy on either side. Now we look at the area ratio, which we get from the conservation of mass. So we know conservation of mass. Okay, that's better. We know conservation of mass is rho AV. Well, rho 1A 1V1 equals rho 2A 2V2, which can be expressed in terms of specific volume as and I'll put a strike through the V's for velocity. A1 V1 over specific volume 1 is A2 V2 over specific volume 2. All right. The V's cancel because they're the same. We're told the inlet is the exit velocity. And specific volume wise, well, we know for an ideal gas, let's put a little side note here. For an ideal gas, pressure equals rho RT, which can be expressed, that means that pressure times specific volume equals RT, which means that specific volume is RT over P. So with what we do here, let's bring the A's to one side and the V's to the other side. And now substituting this, we get A1 over A2 equals RT1 over P1 divided by RT2 over P2. So R's canceled because it's the same gas, so R's canceled. We just found that in this case, T1 is T2, so those cancel. And then we're going to go here. we're going to end up with A1 over A2 equals P2 over P1. So the answer to the question, the area ratio is the pressure ratio. Now, in this question, if you look at the solutions, the assumption done is that the exit is atmospheric pressure, which is 100 kilopascals. So if we work through it that way, A1 over A2 equals a P2, which is 100, which is atmospheric pressure at standard at sea level. And we're given 1200 kilopascals or 1.2 megapascals. So basically what we see is that A1 over A2 is 1 over 12, or in other words, the exit area is 12 times as large as the inlet area.